topic of partial differential equations is a really important one for mathematics and engineering and science, and it covers a huge array of different phenomena, from waves propagating across the surface of the ocean to heat diffusing throughout a building. In this lecture, we're going to see that we can think about partial differential equations a lot like the way we've thought about ordinary differential equations. That is, a partial differential equation, or a PDE, is an equation that involves a function of more than one variable and its partial derivatives, just like the way an ordinary differential equation is an equation involving a function of one variable and its ordinary derivatives. Just like ODEs, in a PDE we need to fix the solution or to add information from the initial conditions or boundary conditions. And just like with ODEs, to solve partial differential equations, we're going to have to look at the type of PDE that we're looking at. So in this lecture, we're going to see how to categorize partial differential equations, and we're going to see two simple methods for solving them: partial integration and D'Alembert's solution. Next lecture, we'll look at a much more general method for solving PDEs, the method of separation of variables. So we're going to start by looking at some examples of partial differential equations. We've got what's known as the one-dimensional wave equation, the one-dimensional heat equation, the two-dimensional Laplace equation, and then we have some arbitrary partial differential equation in example 4. In each of these, we see that we have a function u that depends upon two variables: u of x and t, u of x and t, u of x and y, and u of x and t. X is going to be our space variable, our distance along a line or distance across the ocean, and t is our time variable, so how much time has gone by. Looking at the one-dimensional wave equation, we see that we have a second-order derivative with respect to time, so partial derivative with respect to time, equals some constant c squared times the second-order derivative with respect to space, with respect to x, the distance. We've got the one-dimensional heat equation, which looks very similar, except it's got a first-order derivative for time. We've got the two-dimensional Laplace equation, which also looks very similar, except instead of having c squared d squared u dx squared, it's got two derivatives with respect to space variables. And then we have a more complicated expression here. Now, in order to figure out solutions for these equations, we need to know what type of equations we're looking at. And we're going to do that by looking at the order of the equation and whether it's linear or nonlinear. So when we look at the order of the equation, what we mean by that is the highest order derivative. Just like with ordinary differential equations, the order of the differential equation is given by the highest order derivative. So the one-dimensional wave equation, its highest order derivative is d squared u dt squared, or d squared u dx squared, so this is a second order equation. With the one-dimensional heat equation, we've got a first order derivative with respect to t, but we've got a second order derivative with respect to x, and it's the highest order that matters, so this is also a second order differential equation. Likewise, with the Laplace equation, I've got two second order derivatives. This is a second order equation. Looking at the fourth example, you see I've got a partial derivative with respect to t and a partial derivative with respect to u. So even though this partial derivative with respect to t is squared, it only involves the first order derivative. So this is a first order equation. The other important way of categorizing partial differential equations is by determining whether they're linear or not. That is, does my equation involve u, or du dt, or d squared u dt squared, or du dx on its own? It only involves a single u. So in each of these cases, the one-dimensional wave equation, one-dimensional heat equation, and the two-dimensional Laplace equation, you see I involve only u here, u, or d squared u dt squared. There's no products, there's no multiplication u times u, or u times du dt. In the last example, example 4, I've got d squared u dt squared. So this is du dt times du dt, so this is not linear. So we can see that 1 through 3 are all second order linear differential equations, whereas the fourth example is a first order nonlinear partial differential equation. Now with partial differential equations, like with ordinary differential equations, we're not going to be able to fully solve the problem unless we have extra information. That's going to come from initial conditions or boundary conditions. Initial conditions are going to tell us the value of our function u at some initial time, t is equal to 0. Boundary conditions are going to tell us the value of u at some specific point, at the edge of our domain. X is equal to 0, for example, and x is equal to L, for example. Now we have some general methods for solving partial differential equations. And the simplest method is partial integration. Sometimes that'll work, so let's take a look at that. Example 1. We've got an equation d squared u dx dy, so a mixed derivative dx dy, is equal to cosine y. So u here is going to be a function of x and y. This is a second order differential equation. It's got a highest order derivative of d squared u dx dy, so it's a second order derivative, the mixed derivative, and it's non-linear. I've got cosine y here. Sorry, it's linear. I've got just d squared u dx dy. It doesn't involve u squared or du dy or anything like that. So this is a linear second order differential equation. So the way that I'm going to solve this is by integrating both sides with respect to x. And when I do that, I turn my derivative here, d squared u dx dy, it just gives me d squared u dy, du dy. So it eliminates one of my derivatives. I get to the right-hand side here, the integral of cosine y with respect to x. Well, y is going to be treated like a constant, so that's going to give me x cosine y. And I also need to include a constant of integration. But because this is partial integration, that constant could depend upon the other variable. I'm integrating with respect to x, so this could depend upon y. Next, I'm going to integrate with respect to y. Once again, integrating with respect to y is going to get rid of my partial derivative. I'm going to treat x like a constant for the purposes of this integration, so I'm going to get minus x sine y. I've got the integral of c y dy, and I've got another constant of integration. But just as in the last case, that constant of integration, because this is partial integration, could depend upon the other variable. So this can depend upon x. Now you notice here that I've got the integral of cy dy. Well, that's just going to be yet another function of y. So I end up with the following solution. Minus x sine y plus psi y plus phi x. Psi y plus phi x. And phi and psi here are unknown functions of x and y that are going to have to be determined using initial conditions. So we're going to see in solving partial differential equations that boundary conditions and initial conditions play a really important role in forming the solutions. Now, before we look at more complicated techniques for solving differential equations, partial differential equations, let's see how we can verify that we have a correct solution. So let's say I have a solution u of x and t is equal to e to the minus t sine 3x, and I'd like to verify that this is indeed a solution for this equation here. This is the one-dimensional heat equation. So what I do is I simply substitute my solution into that equation by taking derivatives. So I've got my function u of x and t is equal to e to the minus t sine 3x. I can take the partial derivative or using the shorthand notation u subscript t. That's going to give me minus e to the minus t sine 3x. Likewise, I can form the partial derivative with respect to x. Again, I'll use the shorthand notation u subscript x is the partial derivative with respect to x. That's going to give me 3e to the minus t cosine 3x. And I can form the second partial derivative with respect to x, or u subscript xx is going to give me minus 9 e to the minus t sine 3x. So now I can substitute all of those expressions in. So I have du dt is equal to e to the minus t sine 3x. That's my left-hand side. And my right-hand side is equal to 1 over 9 d squared u dx squared, which is going to be equals to minus, there's a minus sign there, minus 1 over 9 e to the minus t sine 3x, which is equal to minus e to the minus t sine 3x. So we found that u of x and t is equal to e to the minus t sine 3x is indeed a solution, because when I substitute it in here, it balances both sides. Now, we're going to look now for the rest of this lecture at a very specialized way of solving the wave equation, the one-dimensional wave equation. So let's first of all take a quick look at that. We've got d squared u dt squared is equal to 25 d squared u dx squared. And you notice that this is of the form, the general form for the one-dimensional wave equation, d squared u dt squared is equal to c squared d squared u dx squared, except that c here has been replaced with 5. So this is the one-dimensional wave equation. It's going to describe how a wave moves along a string. So my solution, u of x and t, is going to tell me the displacement of that wave at a particular value of x and a particular value of t. So if I imagine a guitar string and I pluck the guitar string, then I'm going to see a wave propagating that's going to tell me how far that string has been displaced. In exactly the same way, I could think about a wave propagating across the ocean. In that case, u would be the height of the ocean, so the deformation of the surface of the ocean, and then u of x and t tells me how that deformation, how the height of the ocean is changing with time and space. Now we're going to use D'Alembert's solution to solve this one-dimensional wave equation. So let's take a look at D'Alembert's solution. It's given at the front page of your notes today. This is the general solution of the one-dimensional wave equation. And again, it's called D'Alembert's solution. This is not going to work in all situations. It's only going to work for the one-dimensional wave equation when I have an infinitely long string. And it has the following form. I've got u of x and t is equal to some unknown function phi. So just in case you're not familiar with that symbol, that's pronounced phi. And an unknown function psi where phi is a function of x plus ct and psi is a function of x minus ct. So you might say to yourself, why does that actually improve my solution? How is this helping me? I don't know what phi is and I don't know what psi is. Well, in the process of using D'Alembert's solution, we're actually going to find out what phi and psi are using some initial information about our system. What was the initial pluck of the string? What was the initial shape of the wave in the ocean or the pond, for example? When I throw in a pebble, the pond is deformed, the surface of the water is deformed. And an interesting thing that you notice about phi and psi here is they're actually functions of one variable only. So phi is a function of u, and psi is a function of v, where u is equal to x plus ct, and v is x minus ct. So what we find here is that our solution is going to be written as two variable functions of one variable. So I've taken a function of two variables and written it as the sum of a function of one variable and a function of one variable. And that's going to be really useful in terms of solving this equation. So this is our assumption, and we're going to then substitute that in to see if it works and find out what the consequences of that are. So what we're going to do is we're going to just make an assumption about the solution that it takes the form of D'Alembert's solution. So we're going to assume that our solution y of x and t can be written as phi of u plus psi of v, where u is equal to x plus ct, and remember c in this case is 5, and v is x minus ct. So again, c in this case is 5. So that's an assumption. We're going to have to figure out what the form of phi and v are by substituting this expression now into my wave equation. So here's our wave equation at the top. I'm going to do that by using my initial information here. So let's put a little box around the initial information. We're told that the initial displacement is this, and the initial velocity is this. In other words, I'm told what the value of u is when t is equal to 0, and I'm told what the partial derivative of u with respect to t is when t is equal to 0. So let's use this information. So I've got u of x when t is equal to 0 is 6e to the x. Now what does that mean for our solution? Well, I'm going to substitute t is equal to 0 into this expression. Remember that phi is a function of u, and u is a function, I guess I shouldn't use u there because I've already got u, so let's use v and w. v and w. So I don't want to confuse u of x and t here with v and w, the dependence of phi and psi. Okay. So I've got phi is a function of v, and v itself is a function of x and t. And I'm looking at the value of this function when t is equal to 0. Psi is a function of w, and w is a function of x and t, and I'm looking at t is equal to 0. So what are v and w when t is equal to 0? Well, here's our expressions. When at t is equal to 0, v is equal to x plus 0. It's just equal to x. And when t is equal to 0, w is equal to x minus 0, so it's also just equals to x. So I get here phi of x plus psi of x. So this is interesting because now I've got an expression here for phi of x plus psi of x. Everything just involves x. There's no mention of t anywhere. So I'm going to put a box around this and call it equation 1. We're going to make use of that equation to solve for phi and psi. But I need another piece of information. I'm going to need to use the initial velocity, that is the derivative of u with respect to t when t is equal to 0. So first of all, let's take a look at the partial derivative of u with respect to t. Remembering that u is equal to phi v plus psi w, I'm going to need to make use of the chain rule. So what's the derivative of phi with respect to v? It's going to be the derivative of phi with respect to v times partial derivative of v with respect to t, and the derivative of psi with respect to t is going to be the derivative of psi with respect to w times the partial derivative of w with respect to t. So here I just used the chain rule. Now, what is dv dt? Well, let's take a look at our expression again. V is equal to x plus ct, or x plus 5t, so dv dt is just going to be 5. Likewise, dwt dt is just going to be minus 5. So I'm going to write that as d phi dt times 5 plus d psi dt times minus 5. Sorry, that's d phi dv. There we go. Now notice here that I've got the derivative of phi with respect to v, and I've got the derivative of psi with respect to w. So I've actually got the derivative of a function of one variable with respect to its variable, and I've got the derivative here of a function of one variable with respect to its variable. So I can write that using a shorthand notation, phi prime at x minus 5 psi prime at w. So here, prime here just means I'm taking the derivative of phi with respect to its argument v, and prime here means I'm taking the derivative of psi with respect to its argument w. Okay, so now I'm ready to evaluate the partial derivative of u when t is equal to 0. So it's going to be given by 5 times phi prime v depends upon x and t, and I'm looking at t is equal to 0, minus 5 times psi prime w depends upon x and t is equal to 0. And we've already seen that v when t is equal to 0 is just x, and w when t is equal to 0 is equal to x. So I've gotten here another equation for phi and psi, specifically an equation for their derivatives. This is equal to the partial derivative of u with respect to t at t is equal to 0. It's equal to this initial condition, and that's given to us here. It's equal to 10 cosine x. So that's our second equation. I'm going to put another box around that. Or in fact, if I divide both sides by 5, it looks a little bit nicer. I get an equation involving phi and psi and cosine of x, and I'll call that equation 2. So now I have two equations for my two unknown functions. Phi plus psi is equal to 6e to the x, and that came from the initial displacement at t is equal to 0. and phi prime minus psi prime is equal to 2 cosine x, and that came from the initial velocity at t is equal to 0. Notice that these two equations are equations for the unknown functions phi and psi, but they only involve the variable x. They do not involve t. So what I'm going to do is I'm going to solve these by integrating, or rather by differentiating equation 1 with respect to x. So I'm going to take the derivative with respect to x of equation 1. What does that give me? Well, equation 1 was phi plus psi, so that's going to give me phi prime plus psi prime is equal to 6e to the x. The derivative is equal to 6e to the x. So taking the derivative of this thing. And now I can add together those two equations. See that I get cancellation between the phi primes. And so I get the following expression for phi prime. Phi prime x plus phi prime x is equal to 2 cosine x plus 6e to the x. So this is an equation for phi prime. I could divide both sides by 2. And to solve this equation, I'm just going to use integration. Integrate both sides with respect to x. So I'm going to get sine x plus 3e to the x plus some unknown constant of integration. I can also get phi from this because from equation 1, so equation 1, remember, was phi x plus psi x is equal to 6e to the x. So that implies that psi x is 6e to the x minus phi x, which is going to give me, we get 6e to the x minus 3e to the x is going to be 3e to the x minus sine x minus c. So let me gather together my solutions. I've got phi is equal to sine x plus 3e to the x plus c. I've got psi x is equal to minus sine x plus 3e to the x minus c. So I found the forms of my solution phi and psi. Now, remember that our assumption was that u of x and t was equal to phi x plus ct, c is equal to 5, plus psi of x minus ct. So that was what our value of our function was for all values of t. But our functions here, our solutions for phi and psi, are given for x, not for x plus 5t or x minus 5t. So to substitute these expressions in here into this expression, I'm going to need to just replace everywhere I see x with x plus 5t or x minus 5t. So phi of x plus 5t is just sine of x plus 5t plus 3e to the x plus 5t plus a constant, that doesn't change. And I've got psi of x minus 5t is equal to minus sine x minus 5t plus 3e to the x minus 5t minus c. So you can see that all I did there was I replaced x everywhere it appears in these two expressions with x plus 5t for this function and x minus 5t for this function. So now I'm ready to substitute these in to find D'Alembert's solution. Phi was sine x plus 5t plus 3e to the x plus 5t minus c. And psi was minus sine x minus 5t plus 3e to the x minus 5t minus c. Sorry, that was a plus c, that's a minus c. So we see that the c's cancel, leaving me with the solution sine x plus 5t plus 3e to the x plus 5t minus sine x minus 5t plus 3e to the x minus 5t. So we have a kind of a complicated looking solution here, but we can verify that it's a solution by substituting it into our original differential equation. So I'm going to do that by taking derivatives. So check. What is u partial derivative with respect to t? So that's going to give me, using the chain rule here, I'm going to get 5 cosine x plus 5t plus 15e to the x plus 5t minus 5 cosine x minus 5t minus 15e to the x minus 5t. So just using the chain rule there to evaluate the partial derivative with respect to t, let's do it again. I'm going to get minus 5 times 5 sine x plus 5t plus 5 times 15 is 75 e to the x plus 5t minus 25 sine, actually it's a plus 25 sine x minus 5t plus 75 e to the x minus 5t. So that's my left-hand side of my equation, of my partial differential equation. The right-hand side is going to be given by 25 times the second derivative with respect to x. So I'm going to do that in one step. You can check that yourself by calculating u partial derivative with respect to x and then another partial derivative. But what you're going to find is that the solution becomes minus so we're going to get minus, let's take a look back at our u of x and t. Here it is here. U of x and t, so the two derivatives is going to pull out a minus sign. I'm multiplying everything by 25. Two derivatives of this is going to pull down 2 factors of 5. And I'm multiplying it all by 25. Sorry, it's going to pull down x, so it's not going to pull down anything. So I get 25 e to the x plus 5t. I've got plus 25 sine x minus 5t, and I've got plus 75 e to the x minus 5t. So we get left-hand side equals to right-hand side, so this is indeed a solution. Okay, so how can we understand where this solution comes from and what it actually means? So to do that, what I'm going to do is I'm going to look separately at phi and psi. So here we go. Let's look at u of x and t is equal to phi x plus ct plus psi x minus ct. And again, c here is equal to 5. So let's look at the first part. We saw that this was phi so when t is equal to 0, phi of x plus 5t is just equal to phi of x. So that was one of our initial conditions, right? So I have some distribution with time. So let's sketch distribution with space. So let's say phi of x looks something like this. And this is when t is equal to 0. Now what happens when t is equal to 1? So we've moved forward 1 second. In that case, phi of x plus 5t is equal to phi of x plus 5. In other words, I've shifted my function by 5 units. So my function is going to now, I've shifted my function over 5 units, so it'll look something like this. It's been moved over by 5 units. And likewise, if I keep on going, you can see that every time I take a step, this solution is going to be moving over by 5 more units. What happens for psi? Well, let's take again a look at t is equal to 0. Psi of x minus 5t is just going to be psi of x. So again, I could just imagine that my solution starts off looking like some sort of little bump in the middle. And that's at t is equal to 0. And when t is equal to 1, I get psi of x minus 5. So my solution has been shifted over to the right. By 5 units. So what's happening here is that my full solution is going to be the sum of 2 pieces. One piece that just takes my original solution and makes it move over by 5 units every second. 5 units, 5 units, 5 units. And the other piece which makes my solution move over 5 units to the right every 5 seconds. 5 units, 5 units, 5 units. So imagining again in terms of some sort of string, for example, and I'm plucking my string, so I've caused some sort of deformation. What happens after that? Well, I'm going to have 2 solutions, basically 2 waves propagating away from one another. Another way to think about it would be in terms of water waves. So you can imagine looking at water waves, and I drop a stone in, that causes some sort of deformation, and then that deformation is going to move apart from the center, just like a pebble being thrown into a pond. So D'Alembert's solution is a solution that involves 2 traveling waves moving in opposite directions with the same speed. So they're propagating or moving in opposite directions with the same speed. And that speed is given by c, which appeared in our wave equation as the constant that was multiplying the second derivative with respect to x. So here's our wave equation again. C here is the square root of 25, so it's 5. And that's going to be determined, for real system, that's going to be determined by the properties of the material itself, or the thing that's being oscillated. So how tight is the string, what material is it made of, how dense is the water, and so on. That's going to determine the speed of the waves propagating. Now we can look at a more general scenario. What happens if I'm given that the initial displacement is f of x? Well, we saw that just going through the same process again, that's going to give me phi of x plus psi of x is equal to f of x. And let's say that we're told that the initial speed is g of x. So again, going through that same process again, we would find that phi prime x minus psi prime x, all multiplied by c, is equal to g of x. And that's coming about because phi is equal to phi of v, and v is equal to x plus ct, which implies that the derivative, the partial derivative of phi with respect to t is going to be c times the derivative of phi with respect to its argument. And likewise, psi is equal to a function w, where w is equal to x minus ct. So the partial derivative of psi with respect to t will be minus c psi prime w. So we end up with two equations here involving phi, psi, f of x, the initial displacement, g of x, the initial velocity, and the speed, c. So in a general case, we can actually solve for phi and psi here in terms of f of x and g of x. So for example, if g of x was equal to 0, if the initial speed was 0, then we would have c times phi prime of x minus c times psi prime of x is equal to 0. So I could actually cancel out those factors of c. I could take my equation for f of x here and take its derivative to get phi prime x plus psi prime x is equal to f prime x. Add those together, cancel out the psi primes to get an equation for phi prime x. Integrating that with respect to x would give me phi of x is equal to 1/2 times f of x plus some constant of integration. Likewise, using my equation, number these, so that's 1, this is 2. So I used 1 here. And using 1 again, I can find an equation for psi. Psi of x is going to be equals to f of x minus phi x, so that will give me 1/2 f of x minus c. And so my full solution is going to be phi, but replacing everywhere I see x with x plus ct, plus psi, but replacing everywhere I see x with x minus ct. And that will be given by 1/2 f of x plus ct plus 1/2 f of x minus ct, and the constants of integration would cancel. So that would be the solution for the case when g is equal to 0. And you can look at more general cases as well. Now, D'Alembert's solution is a very specialized method for solving the one-dimensional wave equation when the material you're looking at is infinitely long. That is, I'm looking at an infinitely long string, or I'm looking at an infinitely wide ocean. So what is the propagation of a wave when it doesn't interact with any boundaries? In the next lecture, we're going to look at the case when I've got a string or a water surface that's fixed between two boundaries, and ask what happens when I pluck that string, how does it change in space and time? And to solve that, we're going to use a much more technically involved but much more general technique called the method of separation of variables.